के अंदर हो जाए मार्केट तक तो अगर हो
रजनीश रजनीश
हम लोगों ने क्या किया फिर जो है गाड़ी से चले क्या पैदल चले तो उन्होंने कहा कि जो है आएगा नहीं अभी आप डेट जो लगे आप लगवा लीजिए खड़े हुए थे तो उन्होंने कहा कि महिला का डिसाइड कर दिया जाए ये केस जो है काफी वो है इनका टेन्यूर खत्म हो रहा है और इसमें बहुत सारे केस लगे हुए हैं
डॉक्टर रमाशंकर जी
यस सर नमस्कार सर Yes, sir. I am listening. Your wife is. Yes, sir. I am unmuting my. Okay, sir. Just I made a call. Just I have a salute. Okay.
Okay. Good afternoon, all participants. Rajnish, my voice is clear? So, dear participant, good afternoon to all of you. Today, our notable speaker is Dr. Satendra from Sejong University, South Korea. He is an expertise in X-ray crystallography, and he is always our mentor or our guide in the area of research, and we always respect him. And Dr. Singh is a very renowned person in the area of crystallography. And I introduce him that sometimes Dr. Singh have done MSc in physics from the University of Allahabad and MTech in Materials Technology from IIT VHU Varanasi, where he was awarded with the gold medal. He has received his PhD degree in Material Science and Technology from IIT VHU Varanasi in India 2009. After receiving his PhD degree, he has worked as a postdoctoral researcher 2010 to 2013 in the Department of Printed Electronics Engineer at Suncheon National University, South Korea. Currently, he is working as a research professor in the Department of Nanotechnology and Advanced Material Engineering since 2013 at Sejong University, Seoul, South Korea. Dr. Singh has very vast experience, nearly 20 years in the area of X-ray powder crystallography, phase transition, functional material. His research interests comprise an extensive range of aspects in the field of material science, functional ceramics, phosphor materials, multiferrics, dielectric, ferroelectric, piezoelectric, light emitting, diode, battery materials. His research is mainly based on structural characterization, complex inorganic material using different diffraction techniques such as X-ray powder diffraction, neutron diffraction, electron diffraction, and transmission electron microscopy, scanning electron microscopy, and structure property correlation using this technique. He has discovered several novel phosphor material for application in white light emitting diode and display devices. He has discovered and registered several compounds as new structure type that has never been reported before the ICSD database. He has published more than 55 research articles in international journals, and his research has been very well received and heavily cited by the other researchers. He has nearly 1400 citations with H index of 21 to his credit. Some of most prestigious journals in which he has published his research articles include Nature Communication, Scientific Report, Advanced Energy Materials, Journal of the American Chemical Society, Interfaces in Organic Chemistry, American Chemical Society, Journal of Metal Chemistry C, Physical Review V, Applied Physics Letter, and so on. So,
okay, thank you, Lakshman. Thank you very much for giving me this opportunity. And today lecture I have planned so that it can be interested for the people who are working in the field of the crystallography, particularly the students who are little familiar about the crystallography, and especially for the people who are working in the field of material science. As we know, so I'm going to share my presentations. So,
okay, sir.
Okay, so here is okay. Share screen. Okay. Okay, I hope it's visible, right?
Yeah, yes, sir.
Okay. Okay. So the topic of my talk is the basics of powder X-ray crystallography and its application in material science. As you know that everyone is fascinated about this beautiful looking crystals, and only we are more fascinating because of this the shyness nature, and it's light coming from the different faces. But it was the actual inherent properties and the actual the atoms which are constituting these kind of crystals were little known until the discovery of the X-ray by Röntgen in 1895. That was a very great discovery, and for which he got the first Nobel Prize in Physics in 1901. After the discovery of this X-ray by Röntgen, the famous scientist Lave, he measured the wave nature of the X-ray. And he found that when this X-ray is passed on some materials, it gives some diffraction spots, but he was not able to totally understand the structure using this X-ray techniques. But that also proving the wave nature of this X-ray was a great discovery for which he received the Nobel Prize in 1914. In 1915, the father and son, like William Henry Bragg and William Lawrence Bragg, they determined the crystal structure by using the X-ray discovered by Röntgen, and for which they received a Nobel Prize in 1915. So in this X-ray crystallography, there is large Nobel Prize obtained in different fields, studying in the inorganic materials, organic materials, and the biological materials, and so on. So I have planned my lectures on this part of X-ray crystallography. And the plan of lecture is that first I'm going to just talk about the crystalline and amorphous materials, some basic of crystallography, so that we can. So as we can see, this is a silicon oxide like glass. And if you heat a glass, it will not melt, it will soften. So that doesn't have the sharp melting point as like a crystalline materials. And they have got very short range ordering. Ordering might be there, but very short range. While the crystalline material, they have got very long range ordering. So the amorphous, the terminology, the amorphous, it derives from the Greek word called amorphous, that means no form. There is no form, that is, there is no form, it's formless. It's a short range ordering. So, and if you measure the X-ray pattern of this the crystalline amorphous silicon, you'll have the XRD pattern like something like this. We have a very broad hump for the case of amorphous silicon dioxide, what we call as a quartz, and the crystalline silicon will have a very sharp peaks coming and incorrectly used by synonyms. When we talk of the crystal structure is said to be built of atoms, the real atoms. But a crystal lattice is just a pattern of points. It's infinite patterns of points expanding in the 3 dimensions. So there is no atom all about. So lattice point. So at the lattice point which we talk about may be constituted of one atoms, or it can be a group of atoms. This group of atoms is called a basis. So the basis. So these are the bases. This can be, just remove this basis, just you take out this one, and then you'll get a pattern like this, which is called a lattice. But in the crystal structure, we have actual atoms. So it should be very clear when they are talking about the crystal lattice and the crystal structures. So what does it mean? The crystal structure has actual atoms, while the lattice has it's a pattern, it's a point. Atoms are not present there. So that point could be one atom or a group of atoms or a molecules, and the group is called a basis. So knowing about the crystal things, the most important thing is about the symmetry. So what we know about the symmetry is that if you operate or apply some operations that leaves the object indistinguishable. For example, if you rotate or if you tilt or if you just translate, you cannot distinguish this position whether it was the previous one or the now what it comes is different. So the symmetry is very important in understanding the symmetry is very important in the field of crystallography. So what are symmetric operations are basically is rotation. So where you're performing rotation is along axis. So it can be a rotation one axis along axis, and what we call this axis is the rotation axis. The symmetry can also be like inversion. What is inversion? Just invert. So just along a point, it got inverted. Like the mirror reflections is not actually inversion, but in the inversion, if the point is just x, y, z, then inversion is minus x, minus y, minus z. So there is a center of invergence. And the reflection plane, what happens? So if you see a mirror plane, then the axis is only the axis is reversed. So if you are just put a mirror perpendicular to the x-axis, the x becomes minus x-axis. And the translation. So as we know that the crystalline structures, they are very it's a periodic arrangement. So once you translate one period, we have a similar kind of form. So that is called the translation symmetries. Now along with this, the rotation, inversion, and reflection symmetry, we can have a multiple combined symmetry, like first rotation and then inversion. So this kind of symmetry is called rotation, roto-inversion. That is called rotation, and plus inversion is called roto-inversions. So, for example, people are just maybe some are familiar. Those who like students who don't know, we call the symmetry of rotation as an n-fold symmetry or n-fold axis of symmetry. So what is that n-fold? For example, if you rotate to 2 pi by n about an axis, the bring figure into a congruent positions, and this axis is called n-fold axis. So how many? Sorry. Okay. So how many types of rotations are permissible in the crystallographies? So we can have a one-fold rotations, two-fold rotations, three-fold rotations, four-fold rotations, six-fold rotations only. No five-fold rotations. Okay. So the five-fold rotation is strictly prohibited. So I'm not going to more details because it needs more time to explain why the five-fold symmetry doesn't exist. So the five-fold symmetry doesn't exist. We should be confirmed. So and all the symmetry, rotation symmetry is up to six-fold. And we can have a roto-inversions, and the roto-inversion and it's denoted by 1, 2, 3, 4, 6. And the roto-inversion denoted by 1 bar, 2 bar, 3 bar, 4 bar, and 6 bars. So there are also the symmetry, reflection symmetry. The symmetry of the basis is specified by the collection of symmetric components forming a group called point groups. So in the crystallography, we have symmetry, then comes the point groups. It's the component forming a group called point groups, and in total there are 32 point groups. So if you count these symmetry operations, there are 5 rotations, 5 roto-inversions, that means 10, and 1 mirror reflections, 11. Beside this 11, there are also 22 other point groups, And that 22 point groups are formed by combining one or the two symmetries. Okay, so beside this, and the other terminology what we frequently use is the space group. Now, along with the point group, we have if a glide plane or a screw axis, that is translational symmetries, then it results in 230 space group. So in the crystallography, we have a 32 point groups and we have 230 space groups in the 3 dimensions. So in a crystalline solid, grown in laboratory does not show any 5-fold, as I told, and any symmetry higher than 6-fold. It should be remembered. So the 5-fold symmetry is always absent in a crystalline solid that are grown in the laboratory. But it is important to note that even a crystalline solid can be made that one component can be a 5-fold component, and the repetition of 3 dimensions can lead to a crystalline materials. Other terminology what we should know about the unit cell. So the first we have talked about the X-ray, and then we have known about the symmetry, and then we know now we know about the unit cell. What is unit cell? Unit cell is just like this building block which consists of 3 axes, what we call as A, B, C, and these axes are known as lattice parameters. And angle between this interaxial is alpha, beta, gamma. So lattice parameters are A, B, C, and alpha, beta, gammas. And this unit cell is the smallest portion of the crystal lattice, which when repeated in 3 dimensions, generate the entire lattice. So unit cell is thus the basic structural unit or the building block of the crystal structures. So one should know that depending upon the way how you're defining your crystallography, there may be one unit cell or more unit cell possible to define a total crystal structures. But what we consider is the unit cell of high symmetry. That gives a high geometric symmetry. That is the true unit cells. So there can be possibility of more than one unit cell for a given unknown crystal structures. And this unit cell is of basically 2 types. One we call is a primitive. That means the atoms is only at the corner of this unit cell. Okay, so this is corner of the atom, or if we call lattice, the one lattice point shell. And what is the the corner is called the primitive unit cell, and the other is non-primitive unit cell. That means in addition to this, the points at the corner, there is also point inside the unit cells. So that this arrangement leads to the body-centered. When there is a point as body, if there are points also face, is called face-centered, or some particularly the face like C-centered or S-centered or B-face-centered. So we have different kinds of centering, and this lead to non-primitive or conventional unit cells. This kind of arrangement, okay, so is classified in the different crystal systems, and that are 7 in numbers. So we have a cubic crystal systems. What is specialty about this? The axial relationship is A is equal to B is equal to C, and the interaxial relationship among these alpha, beta, gamma is 90 degrees. So this is the most symmetric in the crystallography when you talk about. And the tetragonal is one of this C axis is not equal to the B axis. Well, A and B are equal, but the angle is always 90 degrees. So this is tetragonal, looks something like this. The third one is orthorhombic. In this, all the interaxial axes are not equal, but the angle is always 90 degrees. So it looks something like that. Then comes the monoclinic axis. Here, all the interaxial axes are different, but alpha and gamma is 90 degrees and the beta is 90 degrees. Here, I'd like to mention that sometimes, depending upon the choice of the cell that I'll discuss later, one can be alpha is gamma can be non-90 degrees and beta can be 90 degrees. So, depending upon the choice, we can choose monoclinic system as the B centering or A centering that will lead to the different conditions for this interaxial axis. Then other is the triclinic. The triclinic is all the cell axes are not equal, and all the interfacial angles are not equal, not equal, and also not 90 degrees. So it can be other than 90 degrees, but not 90 degrees, and they are not equal. And the other is hexagonal systems in which the 2 axes are equal, and the C axis, like the tetragonal, is not equal. But here, one of the angle is not 90 degrees, but it's 120 degrees. So it looks something like this. And the other cell is rhombohedral, in which all these cells are equal. A, B, and C are all equal, like cubic. But The alpha and beta and gamma they are also equal, but they are non-90 degree. So all the cells interaxial axes are equal, and all the interaxial relationships are equal but not 90 degree. So these are the 7 crystal systems which one should know when we talk of the crystallography. Now, as we talk that there are the primitive cells and the non-primitive cells. So the other all the crystal systems, when we combine with the primitive cells and non-primitive cells, then it lead to the Bravais lattice, and there are total 12, total 14 in numbers. If you talk of the cubic, it can be primitive, so all will have a primitive, and then the face centered and and the body centered. So in the cubic we have 3 kind of centers: the primitive, face centered, the body center, I is called body centers. So in total, we have 3 Bravais lattices. In a tetragonal, we cannot have a face centered because one of the axis, C axis, is elongated. So we can have only the body centered or the primitive. So the total number of Bravais lattices is 2. In the orthorhombic, we can all have, even we can have C centering, or C could be A centering or B centering, and F centering, I centering, and it will lead to 4. In total, if you calculate all, including all the crystal system, it will come to the 14. So what we know, we have got a 32 point groups, we have got 230 space groups, and we have got 14 Bravais lattices in a crystal systems. And if you look to the arrangement of the Bravais lattices, this is cubic. So how they say, so this is primitive, this is body centered, this is face centered. Similarly for the tetragonal, this is the body centered, we cannot put the face centered. In hexagonal, we can have a primitive. In the rhombohedral setting, this is orthorhombic, this is C centering, the C axis is centered here, this is body centered, and this is the face centered. Similarly, the monoclinic cells and the triclinic cells. Now, so these all the 32 point groups, they are all denoted by the symbols. So if you see in the triclinic, we can have 1 and the inversion center, that is -1. So we can have a 2-point group and the triclinic systems. In the monoclinic, we have 2-fold rotations, a mirror reflections, and a mirror perpendicular to the 2-fold rotations. So we have total 3. Similarly, in the orthorhombic, we can have 2, 2, 2, 2. It is combined with 3 kind of point groups, MM2, and then total 3 numbers. Total, if you see all together, so it will comes out to be 32 point groups. So all those are shown in different colors. The magentas, which looks in color, are said to be inversion and are called the centrosymmetrics. So all these, the point groups are centrosymmetric. So if you find a crystal structures belonging to this kind of space groups or point groups, then we say that is centrosymmetric crystals. And this highlighted in red colors are said to be termed as an enantiomorphic. So the people working in chemistry, they are familiar with the enantiomorphic structures. So all these 1-fold, 2-fold, and the 2, 2, 2, 2, 4-fold, 3-folds are enantiomorphic, and the magenta colors are centrosymmetric. Besides this, the point group, we also, the people are confused with Lavic class. As we know that all the X-rays, neutron, electron interact with the crystal in such a way that the resulting diffraction pattern is always centrosymmetric, regardless of whether there is inversion center is present or not. So if we have a electron diffraction pattern that is very clear to explain, then if we have a 1, 1, 1 plane, then there is always 1, -1, -1 plane, or 1 bar, 1 bar, 1 bar plane. So there is always a center symmetry. So all these X-ray, neutron, and electron diffractions give the diffraction pattern as centrosymmetric, regardless of the structure is centrosymmetric or not. So this phenomena leads to a crystallographic point group is called Lavic class. So the Lavic class defines the symmetry of the diffraction pattern produced in a single crystal and can be easily inferred from a point group by adding center of invergence. So in total, there are 11 Lavic class. So this is very important when you study the structural, when you characterize the materials and study the structures. So the Lavic class, we have the 11 in Lavic class, and these 11 Lavic class are given the symbol like 1 bar, 2 by M, MMM, triple M, MMM, 4 by M, 4 by M, and 3 bar, like this. So we have 11 Lavic class. We have 32 point groups. We have 14 graphite lattices, we have 32 point groups, and the 230 space groups. Now, if we look at simple metallic structures and say the metallic means if the atoms, how they are lines and how they are contributed. So in the primitive cubic unit cell, we can show in the 3 different models. This is actual atoms, actual crystal structure model it is. So here the atoms lying at the corner of the unit cell, or if you see the whole atoms as in these forms is a close packed structures. And then if you see the contribution coming to the from each atoms will be different. So in this, as it looks, there are 8 atoms in the unit cell, but the net atoms, contribution of net atoms is only 1. Why? Because all these corners are shared with the neighboring unit cells. And in total, we get, so there are 8, 1, 2, 3, 4, and 4. So one contribution is only 1 by 8. So the total is only 1 atom per unit cell. So in case of primitive unit cell, atoms lying at the corner constitutes only 1 atom per unit cell. That's very important to note. Not 8, but it's 1 atom per unit cell. Similarly, in the space center, we will have, along with this, the corner will also have atoms, these faces. And if you just visualize it, it is shared with the neighbor. This atom is shared with neighbor lattice by half. So this is, there are how many faces? 6 faces we have, and each faces share half. So total 3 atoms from the faces and 1 from the corner. So we have 4 atoms per unit cell in case of a face-centered cubic unit cell. While in the body-centered, we have atoms at the corners and 1 atom at the centers. So there are how many atoms? So this is whole contributed to the unit cell, so 1, and then the remaining 1 at the corners. So there are 2 atoms per unit cell in a case of body-centered cubic lattice. So the metallurgists, they are very familiar with this kind of structures. And other important things we need to know is the coordination number. So how one atom is coordinated or bonded with neighboring atoms. So it is essential to know the coordination numbers. And then atomic packing fractions. Atomic fractions is the volume of atom, the unit cell, and the total unit of the volume. So this is called atomic packing fractions, how close the atoms are packed. So that is called atomic packing factors. And it's defined by the volume of the atoms in a unit cell and the total volume of the unit cells. So if we talk about the number of atoms, the coordination numbers, in case of simple cubic, we have 6 coordination number. And the number of atom per unit cell is 1, and the packing fraction is 52. So face-centered have a 12 coordination number, and the number of atoms per unit cell is 4, and the atomic fraction is 74. So body-centered have 8 coordination number of atom per unit cell is 2, and the packing fraction is 68. So if you see this table, we can say that the face center is the most closely packed structures. So if you have something closely packed, means more dense, you will have a higher packing fractions. So we can calculate the density also depending upon these conditions. The density are generally calculated using this formula, so where n is number of atoms associated with each unit cells, a is the atomic weight, and the v is the and n is the Avogadro number. So if you calculate the density, we can say that the face-centered cubic is densely packed because the packing fraction is more here. Then comes the Miller indices. What is the crystal plane? So as we saw that the crystals, the beautiful crystals have different textures when you just rotate, because there are different facets, there are different planes. And how to assign this plane is done by the Miller indices. So and we give the symbol is HKL for each plane. We have HKL from this. HKL is called Miller indices. So if something written in the bracket like 1, 1, 2, that means the H value is 1 and the K value is 1 and the L value is 2. So this is called the Miller indices. And for hexagonal systems, in place of HKL, we represented HKIL, where I is minus H plus K. So this is for the hexagonal system. And HKIL for the remaining crystal systems. All the crystal systems other than hexagonal will have a Miller indices HKL. And for the hexagonal systems, we'll have a HKIL, where I is minus plus K. So Miller indices are represented in this what do you call? This is bracket. So small bracket, what we call, represent not only one plane. So for example, 100 is not only one plane, but it's a set of all identical plane. We can, it can 110, 200, 400, all they are similar planes. So they are set of planes. So when we talk of the SQL plane, they're not a single plane, that is a set of planes. Also, there are other form of notation of the Miller indices. We denote by the braces. This is the braces. And if you write SQL in this form, this is called the plane of the same form. For example, if 100, the braces is closed like this, then in the cubic system, we have 6 planes that are of the same form. In the systems, like 10, 0, 0, 1, and 6 planes of the same form. So it is very essential to denote the brackets appropriately for designing the Miller indices. So let us see, this is a unit cell. If you see this plane is 0, 1, 0 plane. What does it mean? This plane is intersecting the B-axis at the end of this cell. That means whole B-axis. So this is called the and this plane is perpendicular to the B-axis and parallel to the all other axes. So 0, 0 means is the parallel to the remaining axis, and 1 is perpendicular to the given axis. That means the B-axis. If it see 1, 1, 0 planes, that means that plane should be parallel to the C-axis, and it should intersect the A-axis at A and the B-axis at 1 unit. So 1 is 1 unit, whole unit cell. Similarly, this 100, that means this is a plane perpendicular to the A-axis. And if you talk 001, this is the plane perpendicular to the C-axis, and this is 111. This is the plane cutting the C-axis at 1 unit, A-axis at 1 unit, and the B-axis 1 unit. So we can say that all the planes can be assigned using Miller indices with definite numbers. And this bracket used for the notation of this Miller indices are very, 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 very important to take care of. Whether you have to use this is small bracket or this is braces. Other thing is, what you should know is the direction, the crystallographic directions. So the symbol for the crystallographic direction is the square bracket. This is the square bracket, and we denote UVW. So the directions is denoted by UVW general notations, and the Miller indices are denoted by HKL. So this square bracket includes not only one direction, but all parallel directions. So what are the parallel directions? For example, 100, 200, 300, all they are parallel directions. So this represents includes all parallel directions, not one directions. Similar to that Miller indices, where we use braces, we use a bracket notation. This is bracket notation, and this notations means the directions of the same form. That in cubic crystal system, we have, for example, 100 represents 6 directions. That is 100, minus 100, 001, and 10, minus 10, 001, and 00 minus 1. So if you look here, the unit cell, so 100 direction. 100 direction is this one. 100 direction is this one. What does it mean? It is along the axis. So if you write a square bracket, 100, it is along that axis, that is along the axis. While in the case of the Miller indices, 100 means it is a plane perpendicular to the axis. So it should be noted about the directions and the Miller indices. Now with this, the basic informations about the Miller indices, the space groups, the point groups, the Lave class, and all the unit cells, we come to the Potter diffractions. Now in the Potter diffractions, so generally we talk the crystalline solid is a regular arrangement expanding along the 3 dimensions, but the Potters, though they are crystalline, but they are called in the Potter crystallography, we have a polycrystalline, because the small crystals, they are all oriented in different directions. So the crystallinity is limited to these regions, and there are small crystals, several crystals like this. So once we incident a beam of X-ray, it gets diffracted from the similar pairs of the planes, and we have the beams shown here. So this red beam is coming from the similar planes diffracted here, and the green one is coming from the similar plane diffracted in the other directions. So in order to study this kind of phenomena, the diffractions, the all the instruments, they use a particular geometry, and they are called the Bragg-Breen-Turner geometries. These kind of diffractions, they are use the Bragg-Breen-Turner geometry, in which this is X-ray incident at angle omega, and this omega is equal to theta, and so X-ray incident at theta angles, and the detector like at a 2 theta. So the incident angle is omega, is the angle between the source and the sample. This is the sample, this is the X-ray tube, and this is the detector. So the X-ray is incident on the sample through the angle omega, and it is recorded to the detector in 2 theta. This 2 theta is angle between the incident source and the detectors. So depending upon these conditions, there are various instruments which the measure the pattern and Potter patterns, and which looks like this. In theta 2 theta instrument, that is Rigaku, the tube is fixed and the sample rotates at theta degree, and the detector rotates at 2 theta degree per minute. In this this is theta instruments, like analytical experts probe, the sample is fixed and the tube rotates at theta degree per minute, and the detector rotates at theta degree per minute. So depending upon the geometry, one can design whether we can fix the X-ray source, rotate the sample, or move the X-ray source and fix the samples. So all the instruments, based upon their requirement, designs the instrument appropriately. And one of the instruments is like Rigaku Potter X-ray diffractometers, look like this. Maybe people who are not familiar can see. This is in our lab. So here we are using multiple samples only, but generally the sample holder consists of only one. But since we are using some the combinatorial chemistry, so we need so many X-ray at a time, so we can use multiple sample setup, and that this sample get rotated when X-ray beam falls and get detected. So the instrument looks like this. Now, how to get this? Why these X-ray patterns are generated, and what is the law behind it? Is that the Bragg's law. The Bragg's law says that only those X-ray beam will be diffracted which satisfy this Bragg's condition. 2D DHKL sin theta is n lambda. N is integer referred to as the order of the reflections. So other than this, all the incident beam falling on the samples will not take part in the diffraction pattern which do not satisfy these conditions. This is called the Bragg's condition. N lambda is 2 DHKL sin theta. If you see here, in case of X-ray, the initial beam is almost undiminished on passing through the small crystals. The intensity of the diffracted beams are very small, so almost the X-ray beam directly passes through the samples, and a very small portion it is deflected, and this deflected intensity is just is going to the photomultiplier tubes, and we are getting all this information in the XRD patterns. Now, in order to understand the Bragg's law, the n integer, the n is the order of reflection, is very important to understand it. Okay, the first thing, so if you look this Bragg's law, this angle of incident is almost same as the angle of diffractions. The angle of incidence is almost same as the angle of diffraction, and this is similar to the reflection in the light. Although the geometry is very similar to the reflection systems, but it is not actual reflection. This is diffraction, because in case of in the mirror reflections, there is no constraint on the angles. But here, in the case of the X-ray reflections, there is restrictions on the angles. So there is a particular angle at which the X-ray beam will be diffracted and will have a diffraction patterns. And that angle is given by sine inverse n lambda upon 2d scales. So in the and the other parameters in the Bragg equation is the order of the reflections we should understand. Now, if we talk of the first order reflection, that is from, for example, if we have a first order reflection from 1, 1, 1 plane, so it occurred at the angle sine theta, the first order is 1, 1, 1, then we say that sine theta n is 1, n lambda over 2d, 2d 1, 1. Instead of d, we say d HKL, so d 1, 1. Okay. The second order reflection, it can be second order sine theta second order reflection 1, 1 into n is 2 lambda by d 2d 1, 1. So this can be similar to the reflection from the D222. This is the first order reflection from the D22. Similarly, the 333 reflections can be a third order reflection from the from first order reflection from the D333. So we know that the D111, D222, and the D33, D111 is equal to 2 D222 is equal to 3 D333. The equations are almost the same. So instead of using the n, we simply use the Bragg's law as lambda as 2d, not n lambda, but lambda 2d. In place of d, we use the terminology DHKL, and this DHKL is related with the lattice parameter and the HKL values. So the Bragg's law generally used in the form this forms lambda 2 DHKL is sine theta. Now, once we have the XRD patterns, what are the information we are going to extract from the XRD patterns? So, for example, this is the XRD patterns. Generally, it looks in the 2 dimensions. In 1 dimension, we have this XRD patterns. So, what are the information? And we are going to extract from this one, and how this XRD pattern, all the intensity of these peaks are dependent on. So, if you see the intensity of these peaks, they are dependent on the various factors. That is, this scale is called the scale factor. PHK is called the multiplicity factors. This is the Lorentz polarizations. This is the polarization factor. There is absorption multiplier. There is a preferred orientation. There is also extinction multiplier, and this is the structure factor. This is the most important, the factor that define the crystal structure of the materials, which includes the atom types, coordinates, and the thermal motions. So the intensity is proportional to the square of this structure factor. So once you calculate the structure factor, we are able to denote the intensity. And we know that they depend upon the types of the atoms. So the heaviest atom will deflect more because of the having the electron X-rays are deflected by the electrons. So the heaviest atom will deflect more X-rays compared to the lightest atoms. So if you talk about the lightest atoms like hydrogen, it is not deflected by X-rays. So we cannot distinguish hydrogen by using X-ray. So for that case, we use neutron deflections. So in the XRD patterns, we have a peak position, which by knowing the peak position, we'll be able to define the crystal systems when and the unit cell dimension. What are the lattice parameters? What are the crystal systems like? It's the cubic, tetragonal, monoclinic, or what else? And their lattice parameters. And also we can do the qualitative phase identifications. So what are the phases present in that XRD pattern? So the peak position is very essential to know, and that gives this information. The peak intensity depends upon the unit cell content, and what is the occupancy of the atoms, this atomic position coordinates, and the quantitative phase fractions. So peak intensity depends on the few factors: the unit cell content, atomic positions, and the phase fractions. And the other is the peak broadening. The peak broadening will give a crystallized size and a non-uniform microresistance. And the peak profile will give the extended effect like stacking, fault, and disorder. So by knowing the peak position, we'll be able to...
Please mute your mic.
So by
please mute your mic. Okay, Vivian.
Okay, so by knowing the peak positions, we can determine the crystal systems, we can determine the initial dimension, we can determine the qualitative phase identifications. The peak intensity, by seeing the peak intensity, we'll be able to confirm about the unit cell content, atomic positions, and the peak broadening will give like the crystallite size and non-uniform microrestriction, and the peak profile will give the extended defect. So these are all the parameters looking in the XRD patterns are essentials and very helpful in identifying any crystal systems. And what are the analysis we can do from that one? We can do from the powder diffraction method, we can do the qualitative analysis. That means we can do, if there are various phases present or the mixtures of phases present, we can do the phase identifications. Then also quantitative phase analysis. Quantitative, what is the fraction of those phases? And what is the lattice parameter? What is lattice parameter? What are the content of the cells? And we can do the peak safe analysis. That will give us to the crystallite size distributions, microstrain analysis, and we can have so using this powder XRD pattern, we can have a structure solution using direct methods, direct displacement method, and the structure refinement using ripple methods, and the total scattering methods will, like, we can also find the local structures using like a PDF, pair distribution functions. So all these powder reflections are helpful for a qualitative, quantitative, and all the structural informations, the defect, disorders, the crystallite size, and so on. So many informations can be extracted from the product XRD pattern. Sorry. Now, as soon as once we get the XRD pattern, in order to analyze it, the first thing what we do is we have to match the XRD pattern with the existing databases. So there is ICDDD, what do you call the International Center for Diffraction Data. They have numerous, more than 2 lakhs of files, the PDF files, powder diffraction files, where you can match your XRD pattern with the given XRD patterns. And from there, you can know a lot of information, including the lattice parameter, the crystal systems, and also sometimes the references. So the best way to analyze any XRD patterns once you achieve or once you get is to go for the qualitative analysis using the known crystal systems and using the ICDD softwares. So, and to match your XRD pattern using that one and get the information. So once it is matched, you know that, okay, for example, you wanted to synthesize something, some materials in any crystal systems, and that if you get that crystal system, you are very sure that, okay, my XRD pattern is matching with the given one. That means I was able to synthesize the given materials. So that is the qualitative analysis. And the other things the people always use is to measure the crystallite size. So crystallites smaller than 120 nanometers create a broadening of diffraction peaks. This peak broadening can be used to quantify the average crystallite size using Serre equations. So many people, those that are working in the crystallography, they use this Serre equations, where D is the crystallite size and beta is the full width at half maxima. So full width half maximum is just you find the background and then measure the height, and half of this height will give the full at half maxima at the particular angles. But most important thing in measuring the full width at half maxima is you have to subtract the instrumental broadening. For that, you have to calibrate your XRD pattern and know the instrumental broadening. So that instrumental broadening should be subtracted from the given peak. The first thing. Second thing, people always they measure the Serre equation. They apply the Serre equation. They measure the full width half maxima, and sometimes this peak is not a single peak, but it also constitutes of the K alpha 2 measurements. So the first thing, if you have in XRD pattern the K alpha 2, so you have to remove the K alpha 2, and then remove the instrumental background, then obtain the full width at half maximum. Then only your results will come true. Otherwise, you may lead to some false results, and that will not match with your the other the structure obtained from the other methods. So the first thing you do is remove the K alpha 2 if the sample is having the K alpha 2 contributions, because some instrument they already subtract the K alpha 2, but the Rigaku and some other instruments they don't remove the K alpha 2 contributions. So you have to remove the K alpha 2 contribution, and second is to calibrate your XRD pattern to obtain the instrumental broadening. So using this Scherrer formula is very important. And then you can have the crystallite size. You can compare with the same or 10 micrographs. I'm going to just give you an example how to proceed with the how to determine the position coordinate and how to establish a crystal structure if we have only this information. For example, we have the strontium tightness, for example, and the space group is given as a PM3 barium, and the lattice parameter is given, and we know the density. If only 4 information are given, will you be able to generate the crystal system? Will you be able to generate the XRD pattern, or you will be able to generate the atomic coordinates? Will be able to generate the other atomic coordinates? So I'm going to show you how systematically, if you proceed, you'll be only using this 4 information, you'll be able to have a beautiful crystal structures. The first step is to know the number of formula. You have to find the unit cells. Once you find unit cells, then it's done. So you have to know how many formula, like strontium has one strontium, titanium, O3. So how many of this formula is existing in the unit cell? So how you know how you can determine that one using the density, the volume, and the molecular weight. So you can determine Z value. So what is the number of formula unit per unit cell? That is very important. So if you calculate here, so using the formula, we can calculate the Z, and the Z value comes around 0.99, that is close to 1. That means in the unit cell, there are only one formula unit. That means there are only one strontium, one titanium, and 3 oxygens. So the unit cell consists of this. How many atoms? 4 atoms. 1 plus 2 plus 3. Now, we know the number of atoms in unit cells. Now, next step, where they lie in the structure. So we have to find the Y-cup sites. Y-cup sites can be obtained from a Bilbao crystallography server. So if you know the space group, you can find this crystallography table, or also you can use the International Table of Crystallography Volume A. For example, as this PM3 bar M, this is the Y-cup table for the PM3 bar M. And this is multiplicity. That means if you put any atoms at this position, for example, this is called the general multiplicity, and general multiplicity is 48. So if you put any atom at this site, like XYZ, general position is XYZ, you will have a 48 at that sites. So automatically all these sites will be generated. So in the unit cell, you have only one strontium, you have only one titanium, you have 3 oxygens. So we have to look which side we can put those atoms. So if you just go on screening these things, then you will find that, okay, we have 1 atoms. So 1 atoms, okay, this is if I put, we'll get 1 atoms. So 1A, oh, here is also 1B. So which side to put? And then oxygen can be 3 is here. So it can be at the 3C side or 3D side. So there are 2 choices. Whether we can put strontium at 1A sides, or we can put at or 1B sides, or titanium we can put at 1A sides or 1B sides. Then little bit confusions. Then what we have to do? Then let us put strontium at 1A side, and titanium at 1B sides. So which side will be the oxygens? Whether it will be D side or C side, that we'll know. So this is this is a table from the crystallographic server, Bilbao crystallographic server, and this kind of pattern you will get from the International Table of Crystallography Volume A. So you should have this thing. And this is freely available. You can just check from the internet. And this one, if you have the crystallography table, is a big volume of the books, you can generate these things. Okay. So the 4th step is that to denote the sites. Now, if you put strontium at 1A site, then by default, the titanium must go to the 1B side. In that case, we have to measure the bond length by putting the oxygen at 3C sites and 3D sites. So if you put 3C sites, the bond length will come 1.95 angstrom. If you put a 3D sites, so the bond length will come 2.756 angstrom. So yeah, and this is almost 1.95, and this is 2.76. And if you measure the ionic radius you can get obtained from this, online is available. This is from the Abulafia mt.ic.ac.uk. This is Senan tables you can get. So the ionic radii of titanium 4 plus is almost 0.605 in 6 coordination, and ionic radius of O2 in 6 coordination is 1.40. If sum up, it comes 2.005. So you can compare this bond length with the bond length obtained at average side. So 2.005 is very close to 1.95. So the oxygen will go to 3C sides. So strontium goes to 1A sides, titanium goes to 1B sides, and oxygen goes to 3C sides. Other cases, in other case, if you put strontium at 1B sides, that also possible. And then titanium automatically will go to the 1A sides, and the oxygen will then go to the 3D sides. Now, once you know this all occupancy positions in your crystal systems, then you'll be able to generate this beautiful crystal structures. So see, the strontium at 1A sides, titanium at 1B sides, where 3 sides, this is the perovskite structures, titanium lying at here. At these centered positions, and the strontium lying at the corner, and oxygen lying at the face-centered positions. So you will have this kind of perovskite structures. The similar kind of things, if you put the strontium at 1b sides, similar kind of this polyhedra you'll have, and in the three-dimensional space will appear very similar to this. The two figures will appear very similar. Say the oxygen, the strontium is like the whole created by all these octahedra. So in that manner, the very simple structure you can, if you have a very simple structure, you can determine the position coordinates by knowing only the lattice parameters, the space groups, and the density. And you don't need any software to find this kind of study. Now, so now people are always confused. Okay, we have got PM3M space group or I4 by MM space group or something. This the space group symbols they have. Then, how to identify the crystal system from a space group symbol? For example, in the cubic systems, the crystal systems will have a space group like IA3, PM3 bar M or FD3 bar M, etc. So many more are there. So what you have to see, this 3 where it is lying, it's lying on the second position. So in the case of cubic cases, if you see any space group and see 3 at the secondary position, then you say that the structure is cubic. If it is a tetragonal, then you will have structures like P41, 212 or I4 by MM or P4MM, etc. Then there will be a 4 or -4, 41, 42, 4 lying on the primary symmetry position. The primary symmetry position in the first positions. So the first position is primary, this is secondary, and this is tertiary. So in the cubic system, we'll always have a 3 on the secondary positions. In the tetragonal, we'll have a 4 bar, 4, 1, 4, 2, 4, 3, etc. on the primary positions. In the hexagonal cases, we have a 6 bar or 6, 1, 6, 2, 6, 3 on the primary positions. In case of trigonal, we have 3 bar, 3, 1 or 3, 2 in the primary positions. In orthorhombic, we can have like a mirror plane or glide plane, two-fold rotation or square axis will be simultaneously on each position, primary, secondary, tertiary, all of the positions are occupied. In the monoclinic crystal system, this is the short symbol. Actually, this is C1, C1. So in the short symbol, generally used for the monoclinic, we'll have two-fold rotations or screw axis or N glide or the C axis C glide immediately after the main descriptor, that is C means. So P means the primitive lattice. So there is a mirror on the primary axis, and there is three-fold rotations and the mirror in the tertiary axis. So this kind of notation are very helpful for identifying crystal structures from a given space group. So don't get frustrated once you see the space group, you can know the crystal systems. Many people still they report the XRD patterns and they are not familiar with these kind of things. Now, the other important thing is the lattice symmetric directions. In which directions all this the symmetric operations are going to be taken, are going to be done. So in case of triclinic, we don't have any particular symmetric directions. But in case of monoclinic acids, we have the symmetric direction in the B axis. This is called the unique B axis or C axis. So as I told you earlier, while describing the crystal system, that the monoclinic can have alpha is equal to beta 90 degree and gamma not 90 degree, or alpha is equal to gamma 90 degree and beta not 90 degree. That condition will constitute the monoclinic system with a unique B axis or unique C axis. In the orthorhombic, we have we have a symmetry axis along the primary, we have the secondary and the tertiary. All the three axes will have symmetric operations. In the tetragonal, we have the symmetry along the 001 along the primary axis, and 100 or 010 directions along the secondary, and 110 along the tertiary. Similarly, hexagonal 001 directions, that is the direction in the primary axis, and so on. So this the table represents the direction in which the symmetry has to be operated for the given crystal systems. So all this is very important to understand the crystallography, like a space group symbol. You can know the crystal systems. By knowing the space group symbol, you are able to directly tell the crystal system. And also all this the symmetric operations appearing in the space group symbol, we can say which direction is it taking place. Now, how to solve a crystal structure of a unknown system? So if you have a simple systems, then very easily you can index it, and then you can find, okay, first thing you can match it with the given acidity softwares, and then you can know the, okay, my the XRD pattern belongs to this crystal systems, and you will be able to know all the lattice parameters and other things. But once you have a powder patterns or a crystal system which is totally unknown, then how to proceed for that one? So, for example, this is the XRD patterns. This is simple XRD patterns, powder XRD patterns, but sometimes this is very complex and it doesn't matches with the given acidity files. So none of the PDF files or none of this XRD pattern matches with the acidity or any literature available. What you have to do, we have to very systematically proceed to find the structural solutions of such complex unknown systems. The first very step, the structural solutions are, what are the steps required? First, you have to index the diffraction pattern. So, what is indexing?
All is a single name. We all repeat it. That's what we do.
What happened? Anything? Any problem?
That's the point.
Is any question there, Lakshman? Hello. Lakshman, do you have any problem? Any question from there? Lakshman?
We will start here.
Lakshman, are you able to hear me? Hello?
Hello?
Are you able to hear me? Is there any question?
Yes, sir. सुनाई दे रहा है.
Okay. So, if you have unknown systems, then what are the steps involved for the structural solution? First thing is that index the diffraction pattern to determine the crystal system and the unit cell dimension. Second, analyze the systematic absence in order to determine the space group. Then third is full pattern fitting to obtain accurate unit cell dimensions and peak shape parameters. And third, and then input this approximate structural model, allow atomic positions, occupancies, and displacement parameter to define in order to optimize the fit to be matched with the observed diffraction pattern, and this is done in the retrieval refinement. So these are the steps. First, you have to index the systems to obtain the unit cell dimensions, and then you have to, once you index the system, you will have unit cell parameters and all the planes present in the XRD patterns. So you will have the SQL values, and then by seeing that SQL values, you will be able to analyze systematic absence to determine the space group. Once you get the lattice parameters and the crystal systems, you can go for the whole pattern fitting, that is called level fitting, and then obtain accurate cell parameter. After that, if you know some input structural model, then you input it and go for the retrieval refinement. So the indexing process is the very difficult task when it comes to the complex system, because sometimes there may be the peak which appears to be one may be constituted of more than one peaks. So there may be one peaks or overlapping peaks present. So it becomes very difficult task to separate those peaks and then assign Miller indices to each of these peaks. So the indexing process is one of the toughest job in finding the crystal structure of unknown systems. So in the indexing process, is generally now done. Can you please switch off your mic, please? Somebody is.
Hello, participant. Please mute your mic.
Okay. So, indexing is the most difficult process for the unknown systems. When you are able to overcome this indexing process, then things will smoothly follow up. So, in the indexing process, you assign the SQL plane to each of the diffraction plane, and then find the unit cell and the unit cell parameters and the crystal systems. So manually, sometimes it becomes hard to index a system. Then there are several auto indexing programs. They are ITO, Trayer, Dickball, and Melee. So even this indexing with any one program become possible. So one or the other program is going to be helpful to find the initial structure systems and the unit cell parameters. The most easiest of this is trial. This is trial and error methods discovered by the Werner in 1985. So this just gives many trial and then find some probable structure solution, but it is not a deciding. You have to decide. You are the judge to decide whether this given the lattice parameter crystal system is true or not. How to decide that one? Had to see the Terra output. So there are like M20, F20 values. It should be high as possible. So then, and then all the peaks in the XRD pattern should be given index. That means all the peaks should be given HKL plane. So I have that system. So here we index with the lattice parameters 7, B, C, and all the here, none of this, all the given input parameters are well indexed, and we have got very high the F values and the 32 values, and we have indexed that systems, and that systems comes out to be monoclinic. How do we decide monoclinic? Because A is A, B, and C all are different. Alpha is 90 degree, beta is not 90 degree, and gamma is 90 degree. So this system belong to the monoclinic systems. Now then comes questions of finding the space groups. That is another challenge. In order to find the space groups, first you have to find the lattice type, whether it is a primitive or body-centered or the C-centered, or what kind of the what kind of the lattice is present. So the monoclinic. So by indexing, what we infer is that we got the lattice parameter A, B, C, and the beta angles, and we know that the crystal is monoclinic with the lattice parameters, and then all peaks are indexed. So we have the all HKL plane. So we can calculate the D spacing. So this is the HKL, this is the observed and calculated, this is the 2 theta observed value to the calculated values, and then we have the D spacings. Everything is present here. Then by knowing the HKL, what are the HKLs present here, we're going to decide the lattice type. What are the lattice type? What is A type, B type, C type, or primitive types? So next step is to find the systematic. How to do that one? If you see the SQL values of all the index plane, then if you don't find any specific conditions occurring in that given, where you have to see this SQL list. So here 110. So here H is 1, K is 1, 0. So this is odd. 0 is considered as even. So here is this is all odd. Here is even odd. So all even odd kind of things are present here. So now that kind of you have to analyze. So now let us see if there is no such conditions, then that is called the primitive cells. If there is condition, for example, K plus L, that means in HKL values, if K and plus N is even, then we say that is A-centered. If H plus N is even, then we say B-centered. If S plus K is even, then we say C-centered. So based on this systematic absence, we can decide the lattice symbol. So we can decide with the P, A, B, C, F, or if this is all unmixed, that is all HKL are either even or either odd, then it will be face-centered. If HKL is even, if the sum of the HKL is even, then it will be body-centered. If H minus K plus L is 3n, then it is Romanidally centered. If minus H plus K plus L is 3n, then it is Romanidally R-centered in the reverse setting. And if S minus K is equal to 3n, then hexagon is centered. So based on the systematic absence, which is more important, we can decide the lattice symbols. That is whether it is P, A, B, C, F, I, R, or H. Then comes whether there is any translational symmetry, whether there is any glide plane or any screw axis. So for knowing that one, if the K is even, so there is 100 glide. So the symbol is B by 2. If L is 2n, the glide plane is 100 and the translation is C by 2. If K plus L is equal to 2n, then the translation is B by 2 plus C by 2. If the K plus L is 4n, then B by 4 plus C by 4. This is called the glide plane. This is diagonal glide. This is called diamond glide. This is called diagonal glide. So B glide. This is called C glide. This is called diagonal glide. That is B by 2 plus C by 2. And this is called diamond glide. So these are the glide planes. So what is the glide plane is along the 100. What is the translation along the B by 2? And this is called B glide. Similarly, we can have the screw axis. So if H00 is even, if H00 is even, the reflection condition is that H00. So if H is equal to even, then the glide plane is along the axis. So this is along the plane and the screw is along the axis. The screw axis is C axis. So this axis is parallel to C axis. And then the parallel to C axis is the translation will be along the A by 2 and we call it 2 on screw axis. If A by 4, then it's called 4 to screw axis. So the systematic absence will give you information about the lattice centering and the various translation symmetry like glide plane or screw axis presence or not. Then once you know this thing, then you can compare the given information, the lattice centering, the lattice symbol, and then lattice symbol and the lattice parameter and the crystal systems from the space group table available in the international volume of crystallography. So what you do after that, we have to do the retrieval refinement. So what is the goal of the retrieval refinement is to obtain an accurate crystal structure. What is the basic idea of the retrieval refinement? To fit the entire diffraction pattern at once. What do we have to optimize? Optimizing the agreement between calculated and the observed pattern. That means retrieval refinement will generate some calculated pattern based upon your given initial models, and it will try to optimize with the given observed patterns, with the given XRD patterns. What are the quantity minimized is the least square refinement residual SY given by this symbol. So what are the inputs needed to carry out the retrieval refinement is we need to have the correct space group symmetry. We have to have the reasonable accurate unit cell parameters and approximate starting positions for the atoms. That is the structural model. So these are the initial conditions which are required to have the to start the retrieval refinement. So based on our indexing, we find that the space group was indexing. We find that the centering was C, and then space group number we decided N, and the density we calculated, and all this table we generated. And based on this table, we are able to obtain a retrieval fit. We are able to obtain a retrieval fit, which looks like this. So in this retrieval fit, what do we have? So it's a red line. Red line is the calculated line. The black line is the observed line that you obtain from the XRD patterns. And all this, the vertical lines, black lines, the vertical black lines are the positions of the Bragg reflections condition. So if you see these pictures, see very beautiful match. All the red line is coinciding exactly with the black lines, and this is the difference profile, almost nearly a flat difference profile. So the structural model which we have solved is very well matched with the observed profiles. So we can say that the structural determination approach is accurate, and then we have to also verify the certain criteria in the retrieval refinement. These are called the R factors, and these R factors are called the agreement factors. So so we have to see the several parameters, like we have to see the R Bragg factor is called RB, and is given by the intensity of the observed minus intensity of the calculated profiles upon intensity of the observed squared. So these are the sum over all the diffraction spots available in the XRD pattern. Similarly, we calculate the R structure factor, we calculate the R profile factors, we have the R weighted profile factors, and then R expected. Okay, we have the, and then having this parameter, we have to see a deciding parameter we call the chi-square, or also sometimes it's called the S square, and it's given by RWP over RE. What is RWP? Is the weighted profile, and is given by, and RE is the expected value. So N is the number of refined parameter, P is number of refined parameters, total number of points, and these are the YOI is the weight Y, and the YOI is the intensity of the observed data. So all these parameters need to be verified to verify the originality of your refinement. So once you have this kind of fitting and this kind of the table, then you're able to publish your papers. And then once we have the table, we can generate this beautiful the crystal structures. So you can see here. So this crystal structure is generated using Vista program. Is freely available, and all the positions and how the atoms are bonded can be visualized by finding the suitable crystal structures. So based on these techniques, I have developed several novel phosphors. So novel compounds are those that these compounds were not early reported in any of the literature, any paper, or this the crystal structure is not available in any of the structure database. The structure database available is currently the ICSD, Inorganic Crystal Structure Database, or ICDDD, or the open database. So all the structures were non-available, and I solved all the structures, and so we registered in the Inorganic Crystal Structure Database, ICSD. We call it ICSD. If someone claims that my structure is new, then how to verify that one? You can go to the ICSD site. This is not free, but you have to subscribe this one. You have to pay huge amount to get a year subscription, around 600 to 700 euro per year. So we have this access with software access by departmental payment. So if you see, these are some structures which I have solved. And then if you see, this is the structure type. Now this structure is already existing structure type. This structure, no structure type. This is structure type which I saw just was developed my long back, and then now the same structure types that this belongs to. So this is structure type is now well observed by other researchers in the field. Now still this limit this are the vacant site. So now this structure type will transform here once several other researchers are able to find a structure similar to me, which I have discovered. So we have now I discovered nearly 1, and then this is 2, 3, 4, 5, 6, 7, almost 7 new structure type I have discovered and registered in the ICSD database. Now, by knowing the informations like the indexing and obtaining the readable refinement, we will be able to even index the temp pattern, the temp pattern. What do you call this? SAAED pattern, that is the selected area electron diffraction pattern. This is some pattern of some different compound. I have indexed this pattern with index means we have assigned the HKL values to each of this diffraction spot. As I mentioned earlier that in the electron diffractions, this is by nature it is centrosymmetrically. So if this is the origin of this, this is the pattern. So if this is 0 minus 2 bar, then other side will be its inversion. So just put a bar over other side. So just you can find one side and the other will be similarly determined. Now the most important thing is 200. This how do you know that this is 200? In this tempered pattern, you'll get this diffraction spot along with this line. This line is very important. So there are two ways to index this XRD this temp pattern. What is that? First, you can use some software like J images there. Then you can measure this distance, and calibrate along to this distance corresponding to the 1 nanometer inverse. All these diffraction spots is in the reciprocal space, that is 1 by d spacing. So if the d is larger, the this will be closer, more closer. So if d is smaller, it will be more farther because this is in the reciprocal space. This is in the reciprocal space. So now just you measure, or you can do just take the printout of this this temp pattern, measure this distance, and calibrate this distance. Like for example, this is says 3 centimeter correspond to 5 nanometer inverse. That means 1 by 5 nanometers. Then transform into angstrom and then measure. So how much this distance will come out. So then you can measure the d spacing. Once you measure the d spacing, then go to the XRD pattern which you have indexed or which you have refined, and then find what are the scale plane this spacing corresponds. So based on this information, that's two information, you will be able to accurately index the temp pattern. Once you know this the scale values for each and every diffraction spots, you will be able to obtain the zone axis. Will be able to obtain the zone axis. What are the zone axis? Zone axis here is 0, 1, 1. How do I get this zone axis? We can get the zone axis by knowing by using this resistance. Zone axis is given by in UVW is the zone axis given by. So you can obtain is like select any two diffraction spot and the corresponding SQL value and obtain UVW using this relationship. U is equal to K1 L2 minus K2 L1. V is L1 S2 minus L2 H1, or W is H1 K2 minus S2 K1. So any two diffraction spots you obtain, then you can obtain the zone axis. Or in simple way, just you can obtain here, like you just write the two diffraction the patterns like H1 K1 L1 twice H1 K1 L1, and then just S2 K2 L2 and S2 K2 L2. Now do the determinant. So just leave this one, then select this first. So U is K1 L2 minus L1 K2. What will be? Just leave this one. Next, L1 H2 minus H1 L2. Then next. What is next? Then H1 K2 minus K1 H2. So in this way, you can determine the zone axis. So some people just put the diffraction pattern, they don't index it. So once you are very familiar with the Potter X diffractions and you are able to clearly index, or you can or solve the crystal structure, then you'll be able to index any XRD pattern, any temp diffraction pattern. You can and you in order to report this temp diffraction pattern, you need to know the specific knowledge. Simply manually just measure these distances, or you can use the JMS software to do these things. Thank you. Lakshman, if you want, I can. Hello, Lakshman.
Yes, sir.
Yes. Do you want to show me something how to do the indexing, or you want to go with the some question answer?
Participant, do you have any queries and question? Because we have a very good session, because we don't know about the diffraction pattern and time analysis, other things. When you want to ask query and question, then you are welcome. Hello, participant.
Yes, sir. No question. Thank you.
No question. Okay. Any other?
No question, sir.
Thank you.
Okay.
Very good session.
Sir, we can proceed. SP Singh, sir?
So do you want me to show something how they carry the department?
Yes, show me indexing, sir. Indexing.
You want to indexing?
Yes, sir. Yes, sir.
Okay. So I'm going to show you the indexing one. See the indexing. If you have a simple pattern, you can do it manually. Okay. So manually, what you have to do, you have to find the you have to from the XRD pattern, you have to locate every peak positions. Okay. So just you locate. Can I write something, or let me see something which I can show you? Okay, let me show you indexing. Wait. Okay. Please hold on. So let me find something. I'm going to show you a simple pattern so that.
बाबू देखिए
Hello.
Yes, Lakshman, just let me show him some patterns. Then.
Okay. So, sir, you are able to share it?
Yeah, I'll just show you something.
Okay.
Okay. This is the XRD pattern which I was showing here. Okay. So there is a expert software. Those who have a pen analytical machine, it is available with the pen machine. Okay, pen analytical XRD patterns. So if you have this one, so simple thing, you have got the XRD pattern. Then how to index it? Then what we have to do is just you have to first match, is this XRD pattern is matching with any non-compound or not? The initial process. Once you have the XRD pattern, then how to do that one is that
SP Singh, sir, your screen is not visible.
Not visible. Wait. Stop.
Hello.
Okay.
Hello.
Yes.
Yes, sir, Rajneesh.
Now it's coming. Is it visible now?
Not yet, sir. Now you're
Yes, yes.
now yes, now it is visible.
It's gone. Okay, wait. Wait.
Hello?
Yes, yes. Now is it visible?
No.
Yes, yes, it's now visible.
Not visible.
Now it's
Now
starting to sharing. Yes, yes, yes.
now it is visible.
Yes, yes.
That's visible. Is okay. Okay.
Mhm.
So if we have the pen analytical machine, an X-ray machine, this file is easily available. Okay. So if we have, for example, this is XRD pattern and how to index it, and then first we have to compare whether this belongs to some other any given pattern or not. I think this is a little bit. Let me choose some. This is more complex. I think not. It'll be easy to. Indexing. Let me share some other one. Okay. Where is that? Lakshman indexing. Okay. Right. Do other things. I think this will be easy to. Okay. Okay. So, for example, we have this study pattern. Okay. Is it okay? It is visible. Hello, Lakshmi, is it visible? Visible. Okay, okay. So, for example, we have a study pattern. What is the next step? We have to find the peak positions. Okay. So, what you have to do is, see here, we have to detect the peak. So, I'm doing here enable, and then this is auto detect. See, now I'm able to detect the peak position. Okay. All the peak positions is indexed, is marked. Now, what next step is that? Yes, Lakshman.
SPC, sir. Your
Not coming. It's not coming. It's not coming.
PPT is not visible now.
Okay, this I stopped it because it was not going. Now, okay, everybody can hear?
Yes, sir.
Yeah,
Okay.
I am hearing, sir.
Okay,
But
okay,
PPT is not visible, sir.
Is it visible now?
Yes, now it is visible.
Yeah, now
Okay.
It is visible.
So, okay, let us see. So, this is the, for example, a simple XRD pattern. What you have to do, we have to index it. How to index it? We are not talking about any atoms, and I think we don't know anything. Just we have this XRD pattern. The first approach is indexing. What you have to index is we have to first find the peak positions. Okay, we have to find the peak positions. So, how to find peak position? Just I'm going to say this is the peak, and suppose say outer directions. This is the program. So single peaks we can find. Now, see whether all the peaks are marked or not. So there are certain peaks. See, this peaks is not marked. So we have to mark this peak. Right? Okay. This peak is also not marked. Okay. We can mark. The most important thing in indexing is that we have to consider the peak in more peaks in the 2 theta range, in the lower 2 theta range. So, but this pattern has a very few numbers of peaks in 2 theta range. Then we are going to extend this peak position in the little bit high 2 theta range also. And then for indexing, we required at least, if this is a complex system, if it is complex unknown system, then we required at least 20 peaks to index it. But this is a simple cubic system, so there is no enough peaks. Even if you go up to the high 2 theta, that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 peaks are present. Now, next procedure, we have to save this peak. We have to save this peak. So let us save this peak. Save this peak in any. So these are the options like digpol format or ITO format or case search format or terror format. So we can save this peak. Say this is the terror format is the most easiest one. We can save this one in the terror format. Okay, here if to give anything is okay. So remember the wavelength. This was the synchrotron XRD. So a wavelength we have to give it 1.5489. Okay, zero shift is no problem. This is any just we can write any test. Okay, and then 2 theta angles is given here, and then here the unit cell limits. Unit cell limit is we can give any limits up to here is 20, and then 1500 the volume will come around. So this is almost sufficient, and beta maximum is this much, and then okay, therefore the M is okay. So this is just I give okay, and this just give input file. Okay, save, and then do you want to run the terror? Okay, this is the indexing starting. Okay, so this is the synchrotron pattern. Okay, we can give anything, just we can leave it. Okay, so if you look here, the condensed output here. Okay, so once you index it, what you find? See, this is the cell parameter. Cell parameter is 4.011, 4.011, 4.011, and the beta angle is 90, 90, 90 degree. What is the unit cell? Can anybody tell? All the ABC are equal, and the alpha beta gamma is 90 degree. What is the unit cell? Can anybody explain? Tell me. Lakshman, can you tell me? ABC, all the ABC is equal, and then alpha beta gamma is 90 degree.
Cubic.
So from this information, you know that this is a cubic system. Okay, and then next you have to verify that all the, and see, like this is 100. So this is 2 theta is around 22.262. So all these peak positions, like how many peaks were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All is indexed. So the first is 100. Next is 110. After that, this is 111, 200, 2110. So all the things you can get here. See here, number of lines observed is 12. Number of calculated line is 12, right? So what is the F12 values? M12 values is accounted for the 12 peak, too high, 3061. F12 values too high. So this is the accepted solution. Understand?
Understand, William?
Yeah.
Understand, sir.
So see, this is, so from here you know the SQL values, and corresponding to those SQL values, what is the D spacing? D spacing is 4.0115. Okay. So see, 100 plane means, what is 100 plane? This is the A-axis. The plane perpendicular to the A-axis. Okay, so A-axis is how much? Whole unit, 100. How much A-axis? 4. All ABC is equal 4.011. See the D spacing, how much it comes? 4.001015, right? 100 plane. What is the 100 plane corresponding to what will be the D spacing of the 100 plane? It will be equal to the unit cell parameter, right? The D spacing in the unit cell, if you have 100 plane, 100 plane is the plane at the end of the axis. At the, what is the length of the axis? That is 4.001. So what will be the D spacing? The plane, another plane will be at the origin and 200 axis. So what is the distance between the two plane? Is equal to the lattice parameter A, right?
Okay.
A plane, 100 plane, 200 plane, 300 plane. What will be the spacing between them? Will be equal to the length of the axis, right? One A-axis means 100 plane is cutting A-axis at one unit. So it is perpendicular to the A-axis. Next will be 200. Other will be 300. What will be the distance between the two axes? It will be equal to the lattice parameter. So from this indexing, you can clear that, okay, 100 plane, the D spacing is 4.0015. And what was the A spacing? 4.0011. So 4.0015, 4.0015. So your matching is perfectly very good. And other parameter to verify your indexing is this M12 values and F12 values. What is the M12 values? F12 values is 3061 and 1085. Very high. But if you have a complex system, it will be very hard. This is the simple cubic system. So easily you are indexed. Okay. Any doubt on this indexing?
Participant, any doubt?
Anybody wants to know anything about this one?
If you want, you also write in chat box.
Okay, everybody okay? I think they're okay. So there are some queries I just saw in the chat box. I'm going to answer to them. Or anybody wants anything else, just let me know. I can show them some more things. Nobody want anything?
Yes, sir. Explain 100200 clearly.
You don't understand 100?
No, sir.
Okay. Let me. Okay, good. Did you saw my the PowerPoint presentation?
Yes.
So I'm going to show you again that Miller indices. What does it mean? Wait, this program. Let me close the programs all. Then it will be okay. Okay.
Hello.
Hello, sir.
Lakshman ji.
Yes, sir. Good afternoon, sir.
हाँ गुड आफ्टरनून. इसके बाद भी टॉक है?
No, sir. If you want to ask anything, crystallography, because the Dr. S.P. Singh
अच्छा.
is one of
I
the
have
experts.
one question. I have one question.
Yeah, please, you can ask. In the meantime, I'm just opening the slides.
Oh,
Yes,
okay.
please.
So you have shown one example of monoclinic system
Yeah.
where A equals 7.70, but B is very, very away from A and C value. Is it acceptable?
Yeah,
B
it's
is your
always acceptable.
23.87.
No, when the powder get formed, sometimes the shape of the powder is like needle-like. You understand? So it's not uniformly circular. So in that case,
Yeah.
one of the axes is more elongated.
Yes, in compared to other two, it is much more elongated.
Yeah. So it's very common, not uncommon.
Oh, and but in literature, such type of report has not been seen. Usually, these are not reported.
See, all the like simple systems is easy to get like equal, like if you have a cubic systems or very. So if you see the compound, have you seen the compound? Yeah. Okay, let me. What happened to the compound?
And volume is also very large.
Yeah. So if you see the compound, how many atoms are there? Did you see there?
No. Are you showing me something?
Yeah, I'll show you. Okay. What happened to this computer? It's going very slow. Please wait. Please.
Okay, sir.
Okay, we will discuss later. Then you continue your.
It's very common, not uncertain. It's very common.
Yeah.
So sometimes what happens, if you have a very large number of atoms in a cell, then in order to form the unit cell, how these are, how to, you have to get the crystal material, how to obtain this crystallinity. So a small unit cell is not possible to arrange or accommodate all the atoms. So in that case, you have to enlarge the cell. But which direction to enlarge the cell? Sometimes the property becomes directional. So if you have like a platelet or needle-like shapes, then the motifs comes very large to get the periodicity.
But that will be not primitive in itself. That will be not primitive.
It's not primitive. It's a C-centered, not primitive in itself.
Okay.
That is not a primitive in itself.
Okay.
And that sometimes, depending upon the formula units, the number of the formula unit in cell sometimes to be very large. I'm going to show you, I'm going to show you the formula.
And that time beta will deviate away from 90 degree.
Yeah. So it's not deviated?
Away from 90 degree. Beta.
Yeah, beta is always away from 90 degree.
But it may be very close, like 89, 91, like that.
It's very common. We always experience this kind of things. When you get the complex systems, see, if you talk about the metallic systems, which are very well studied and the very symmetric one, then the lattice parameter is almost equal. But sometimes the inorganic complex material, which has large number of atoms, these kind of the things are always observed. If you just analyze ICST data, you have not 1 or 10, you have almost thousands of the data, these kind of things.
Okay, but metallic system it may possible, no?
Metallic system is possible. What you are talking of? But when you go to the complex inorganic systems, then
perovskite structure, like perovskite.
Perovskite is simple structure. Perovskite just like cubic.
Yeah.
So perovskite is very simple. The perovskite is almost cubic, means all the lattice parameters are ABC. If you have a tetragonal, the C deviates only very tetragonality is how much? Not 10%. So yeah. So A is 40, then maybe C is 4.010. So very less.
Yeah, so with respect to perovskite, we are not observing such type of.
Perovskite very simple structures. This is very complex structures. Perovskite things are very, very common. Very small. The axis ratio is very almost like close to 1. Not very large.
Yeah.
Here the B3 axis is very large, and this is very common structures in the complex system. If you go, not one, you'll get thousands kind of structures, this kind of things.
Yeah. Okay. Thank you.
Yeah.
Thank you, sir. Dr. Dev Kumar Mehto sir, also the head of department of
thank you.
physics, IIT Patna. He is also our guide and always helpful to me.
Yeah.
And
So-
he also is joint secretary of this program, faculty development program.
Oh, thank you.
Nice to you, sir, to join us.
Okay, thanks.
Wait, Lakshman, my computer is not working properly.
So we will answer, sir. Any other question?
Oh no, so we should start again. We should continue the
Okay.
presentation.
Okay.
I will. So okay, wait. Okay. Yes. See the composition and atomic tables, sir. Lakshman.
Yes.
But it is not visible. Slides are not visible now.
Not visible now.
Yeah. Please share again.
Okay. I'm going to share again. What is the problem?
There is one question from Dr. Inda Sagar.
Yeah, I'm going to answer. But I'm going to answer. Let me share screen. Okay. Where is the? Okay.
Okay. Now it is visible, sir.
Okay, now you see the number of atom in the here. So the unit cell.
Not visible. Please. 1 second.
Sir, the slide is now visible. I am showing very well. So anybody?
Oh, but in my laptop it is not visible.
Parchment
So
slide is
what I
visible.
have to do?
Now it's sharing.
Now it's visible.
It's visible, right?
Yeah, it is visible, sir. There is no problem.
Okay, again I'll join again.
Okay. So there was another question that he was asking about the what happened to this computer? It's going very slow. Wait, let me close this thing then. Okay. About the Miller. Okay. Okay. This computer has become very slow. This computer is responding very slowly. I'm not able to go. If you can let me open and then let me just I stop sharing and let me open, then I'm going to share it.
Okay, sir.
Yes. What happened? I know it's very slow. Maybe something is updating or what it is doing, I don't know. Okay. Moving. Okay. 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 The person who was asking about the Miller indices. Yeah, he's there. Lakshman, can you hear me?
Yes, sir.
So see, when I talk of the Miller indices, where is the 100 plane? If this is the unit cell, 100 plane will be here. See, look here on the edge of this a-axis, right? Can you see? What does the 100 means? It intersects the a-axis at 1 unit and is parallel to B and C. So see, this plane intersect at a-axis at 100 at 1 unit and is parallel to B and C, right?
Okay, sir.
Where will be the other one? Other will be in the next unit cell. That means 200 will be in the next unit cell, or half. That will be so like 200 will be 200 will be half of this one.
Okay.
So the distance between the two distance between 100 plane, plane will be at origin. For example, this one and this one, the distance will be equal to the a-axis. Then the spacing between the 100 plane will be equal to the a-axis in the cubic system. The distance between 001 plane will be equal to the c-axis. The distance between the 010 plane will be equal to the b-axis in the cubic system. So if you index the lattice parameter a and b and c should be equal to the d spacing, like 100 or 010 or 001. So lattice parameter and d spacing will be equal. That we saw in that case. Is it okay?
Okay, sir. So Bhavneswar Sinha, it is okay. So I think, sir, the participant is satisfied. So I ask Dr. Inta Sagar, are you there? Ma'am, are you there?
लेंथ जो होगा इसमें सर 200 में डबल हो जाएगा. हेलो,
half 200 means what? 200 means what? It's half of it is intersecting at 200 plane, means it is intersecting a-axis at 1/2. Then it will become 200.
again sir.
200 is intersecting a-axis at 1/2. That means half.
Right, this region हम लोग I understood मतलब double. Half you are talking half.
नहीं 200 is Miller indices. 200 means is half intersecting a-axis at 1/2. Then it will become 200. You understand? Miller indices is
reciprocal of Miller indices.
It's a reciprocal of that one. So if you intersect one means half means 1/2. It will become 200.
अच्छा, reciprocal traces.
Miller indices is a reciprocal space. Reciprocal of this intersection.
Now a question, sir.
Yes.
This is please share this PPT. Kindly, I want to share PPT, sir.
I'm going to share it.
Okay. So any other participant, do you have any queries? No, sir.
Let them go ahead.
So thank you, sir, for informative and speaking, sir.
Yes.
So now we are closing the session. So thank you.
Question. Somebody asked me, what is that? How to go for the, just you read in the chat box. Somebody okay, I was asking question, but I was not able to audible. What are the methods can be used to change amorphous solid into crystalline solid? So if you have so how do you obtain a glass? Glass is an amorphous compound. So for example, silicon oxide is amorphous in forms of glass. What you have to do? You melt the glass and do very slow cooling. That may lead to the crystalline material. Very slow cooling. Random same silicon oxide, if it is quenched very rapidly, it will lead to a glass. But if you cool slowly, then it may lead to a crystalline solid. So the cooling rate is very important in deciding the crystallinity of this material. Okay. Okay, Lakshman.
Sir, I want an inquiry. This is the session is like a solid state. और सॉलिड स्टेट में सर चार्ज ट्रांसफर स्पेक्ट्रा होता है या सॉलिड स्टेट रिएक्शन होता है. हाउ कैन यू एक्सप्लेन? हेलो.
See, when you construct the atomic table, In that case, each atom assigned different positions, and you can estimate how many atoms are there. For example, say silicon oxide. What is the valency of silicon? 4.
4.
What is the valency of oxygen? -2.
Yes.
Right? So SiO2 it is charged a neutral compound or not?
Yes.
It's a neutral compound.
Yes.
So if in a unit cell you are going to put a silicon, you have to put a silicon in such a position that the net atom should come 1 and oxygen should come 2.
Yes.
In that case, charge will be balanced or not?
Yes.
So whenever we talk about this crystal structure, the charge neutrality is always taken care of. Otherwise, your structure is not valid.
Yes.
Okay.
Sir. Yes, sir.
So the charge neutrality should be taken care of always. Otherwise, no use. All avoid these structures. Yes. Next question.
Sir, solid state reaction भी solid state reaction.
सॉलिड रिएक्शन, कोई भी रिएक्शन होगा जो कंपाउंड फॉर्म होगा तो न्यूट्रलिटी कंडीशन मेंटेन होगी ना. बिना न्यूट्रलिटी कंडीशन मेंटेन हुए स्टेबिलिटी कैसे आएगी? You cannot have a charged compound.
Yes.
So any compound is neutral in nature, not charged. When it becomes charged when you apply some electric field.
Yes.
Then it becomes charged. Understand? So once the compound is formed, it's a neutral compound. So whatever the structure unit is solved has to be that the charge neutrality condition has to be maintained. Primary criteria.
Yes.
Whether it's solid reactions or chemical reaction, whatever it is happening there, otherwise you lead to the charged compound, ionic compound. तो सॉलिड से बनाइए, चाहे केमिकल से बनाइए, चाहे प्लाज्मा से बनाइए, कभी बनाइए, जो सॉलिड फॉर्म होगा, जो कंपाउंड जो भी फॉर्म होगा, उसमें चार्ज न्यूट्रलिटी कंडीशन मेंटेन होना चाहिए, अदरवाइज नहीं फॉर्म होगा. जब भी स्ट्रक्चर सॉल्व करेंगे, एटम्स को ऐसे पोजीशन पुट करना है कि वो चार्ज न्यूट्रलिटी कंडीशन और नंबर ऑफ एटम्स ऐसे होना चाहिए कि चार्ज न्यूट्रलिटी कंडीशन प्रिजर्व करे, अदरवाइज नहीं करेगा. कभी आपका स्ट्रक्चर नहीं स्टेबल रहेगा. ये प्राइमरी क्राइटेरिया है. बॉन्डिंग जो है ना, एटम बॉन्डेड होना चाहिए, अभी नहीं कि कहीं भी रख दिया बॉन्डिंग उसका आ नहीं रहा. बॉन्ड डिस्टेंस सेटिस्फाई करना चाहिए, केमिकल मतलब चार्ज बैलेंस होना चाहिए, स्ट्रक्चर स्टेबिलिटी होना चाहिए. पॉली प्रिंसिपल्स अप्लाई होना चाहिए, सारे क्रिस्टल सिस्टम अप्लाई होना चाहिए, तब जाके आपका जो स्ट्रक्चर रिजल्ट रिपोर्ट करेंगे तब वैलिड होगा, अदरवाइज वैलिड नहीं होगा, इररिस्पेक्टिव ऑफ सिंथेसिस कंडीशन. ठीक है.
नेक्स्ट सर इसमें आता है एक सुपर कंडक्टिविटी.
सुपर कंडक्टिविटी क्या होता है?
कंडक्टिविटी तो समझते हैं 1/इनवर्स में. जब सुपर कंडक्टिविटी मतलब जब इलेक्ट्रॉन मतलब ज्यादा फ्लो करता है कंडक्टर में.
नहीं, स्ट्रक्चर से सुपर कंडक्टिविटी क्या रिलेट करना चाह रहे हैं
सर? ये सब थोड़ा एमएससी के सिलेबस में मतलब हम लोग का है, थोड़ा बुक्स की जानकारी भी चाहते हैं.
नहीं, तो ठीक है, मतलब सुपर कंडक्टिविटी बुक तो अलग चीज है. मतलब स्ट्रक्चर से सुपर कंडक्टिविटी रिलेट होगा कि इलेक्ट्रॉन्स कितने फ्री हैं, वो तो अलग चीज है. पर सुपर कंडक्टिविटी फेनोमेना अलग है. आप मटेरियल को कूल करते जाते हैं एक डिफरेंट टेम्परेचर्स पे, इलेक्ट्रॉन इतने फ्री हो जाते हैं कि उसको मतलब फिर रेजिस्टेंस नहीं मिलता है, रेजिस्टेंस 0 जाता है और वो कंटिन्यूअसली फ्लो करते रहते हैं. ये सुपर कंडक्टिविटी फेनोमेना है. उसके इलेक्ट्रॉन मूवमेंट के कारण एक मैग्नेटिक फील्ड जनरेट होता है जो रिपेल करता है, जो मैसनर इफेक्ट होता है.
इसमें फ्लोरीन का क्या उपयोगिता होता है सर? फ्लोरीन
किसमें
फ्लोरीन होता है?
फ्लोरीन जो है C40 कंपाउंड्स है, इसमें कहाँ उपयोग करना चाहते हैं आप चीज में?
इसमें सुपर काम करेगा. ये सुपर कंडक्टिविटी कंपाउंड है या नहीं?
अब पता नहीं, मुझे नहीं पता, पता नहीं है मुझको फ्लोरीन है कि नहीं है.
चलिए सर, थैंक यू.
और कोई क्वेश्चन?
नो सर, नो.
Lakshman, shall we wind up now?
Hello.
Yes. Okay.
Hello, sir. SP Singh, sir.
Yes.
SP Singh. So I am audible?
Yeah, you're audible.
So thank you, sir, for informative and valuable talk in this 1 week effort. Participant must avail its usefulness in material. I am thanking on the behalf of organizing committee and myself. Thank you, sir, for joining us. And you,
thank you very much. Thank you.
You are our elder brother.
Thank you. Thank you very much.
You are very thankful to us.
Pal Sahab.
Yes. बताइए.
Okay, thank you very much.
Welcome. Thank you very much.
Okay, we will meet again. Sometimes we will invite you to our NIT Patna also.
And definitely, if I'm there, NIT Patna, Shivendra is there, no? You know, Shivendra.
Yeah. Shivendra is also our colleague. He is our colleague.
And Saurabh Tripathi, he joined IT. He was my just junior.
He was earlier first here.
Yeah,
but he shifted to BHU again.
Yeah, you can ask me about me. Shivan, he knows very well. I have just did his dissertation for MTech one, so he knows.
Okay, Saurabh Tripathi is also regularly talking with me from BHU.
Yeah. So Shivendra was just my MTech 2-3 year juniors. I was doing PhD there. He was doing MTech. So I helped him a lot in getting his thesis done for the MTech dissertation. Then he moved to the IT Kanpur.
Okay.
Saurabh was just just 1 year junior. Saurabh Tripathi.
Okay.
Saurabh Tripathi also did with Professor Dhananjay Pandey. Also did PhD with Professor Dhananjay Pandey. And Shivan did PhD this master thesis with Professor Dhananjay Pandey. So I was his generally, I mean, like an awarded mentor for his MTech thesis. So
yeah.
Thank you very much.
Okay, thank you.
Okay, we'll meet sometime. Okay, definitely.
Okay, thanks. You are welcome. You are most welcome.
Thank you very much. Okay, Lakshman, thank you very much. I'm leaving now then.
Okay, sir.
So, thanks a lot. Thanks a lot, sir. I learned a lot.
Thank you, sir.
Thanks a lot. Actually, I don't like this kind of presentations. When we are one-to-one face interaction, I like it that we can have learn more things. But anyway, no options. So thank you very much for giving this opportunity.
So thank you, sir. So dear participants, and we will meet Monday. And there is one more informative talk on funding research in higher education. As we know that there are lots of agency providing the funding to write project and to submit the proposal. So just we know about 2 and 3 agencies like DST, NCRT, and other things. So, but there are lots of funding agency in research or higher education. So you must join on Monday, 3 p.m. There is a Professor S.K. Yadav, and he is the HOD of NCRT New Delhi. So you must join this program, and we also have validity function and closure on this day.